Hey everybody, let's do some rotational kinetic energy. So let's take a look at a situation. Okay, we have a ramp with some things that we're going to either slide or roll down. So we've got a cylinder of some kind, maybe a soup can, and we have a block, and they're each going to go down the ramp. The cylinder will roll while the block will slide. Never mind how that would actually happen, we'll just make it happen. We might want to know which one would get there first. So we'll also look at a variety of other shapes that roll in relation to AP physics requirements, and we'll go through the calculations that are necessary to figure all this out. So let's take a look at our question. So which object gets to the bottom of the ramp first? So that's looking for a time. And then which object has the greatest speed at the bottom of the ramp? So that is looking for a velocity. And to simplify everything, we'll assume everything has the same mass and radius, should that apply. Okay. So our objects are these 5 things. So we're going to have a block which does not roll. So if it doesn't roll, does that make its moment of inertia 0? It doesn't quite work like that. It's actually a number that's not 0, but we don't need to know that for this particular part. Okay, then we have 4 other shapes that will roll. So we have a hoop where all of the mass is located at the radius away from the center. So this would be like a hula hoop or a hollow cylinder of some kind. Then we have a disc, which is a solid cylinder, okay, uniform mass throughout. We also have a solid sphere, so that would be like a bowling ball if it were uniform. And then we also have a hollow sphere, so that would be something like a ping pong ball, where there's empty space in the middle and all of its mass is located at the radius. Okay, and then these moments of inertia are going to be helpful for us to calculate what's going on later. Okay, so let's start with the easy one. Since we've done this one many times before, let's look at the speed of the block at the bottom of the ramp. So I think speed or velocity is going to be the easiest for us to find first, so we'll do that first because that'll allow us to get to the time a little bit later. Okay, so looking at our block, at the top it'll have gravitational potential energy. At the bottom it's going to have only kinetic energy if we set our gravitational potential at the lowest point. And remember that this block is going to slide without friction. So we're going to use our conservation of energy topics. We get our gravitational potential energy becomes our kinetic energy. We can divide by mass on both sides so that mass is eliminated, doing some algebra, and we get that the velocity of the sliding block is equal to the square root of 2gh, where g is gravity and h is the height of the ramp. When we plug in our numbers, we find a velocity of 6.32 meters per second. Ooh, very fancy. I don't know if that's fast or not. Let's see how it compares with the others. Okay, let's do our hoop first. So there's a lot going on here. So starting at the top. So remember that the hoop is also going to start at the top of the ramp with only gravitational potential energy. And then it's going to roll without slipping down the ramp, which means it's going to have kinetic energy because the hoop is moving, but it also has rotational kinetic energy because it is spinning. In that case, we have to add an extra term for our conservation of energy, which is where we get the rotational kinetic energy. And our conservation of energy equation becomes this, where 1/2 I omega squared is our rotational kinetic energy. Okay, so we need a couple extra bits of information here because we know the moment of inertia of a hoop is mr squared. And we know the relationship between omega, which is the angular velocity, and v, the linear velocity. This relationship was given here, and we can rearrange that so that omega is equal to the velocity divided by the radius. So to simplify things a bit, we can take just our rotational kinetic energy part and substitute in the things that we know. So mr squared for I, the moment of inertia, and then substituting in for the angular velocity, multiplying all that out, and then we have an r squared on top and an r squared on bottom, so that cancels. So the rotational kinetic energy becomes 1/2 mv squared, which we can plug back into our conservation of energy equation. And so on the right side, the after part, we have 1/2 mv squared plus 1/2 mv squared. We have the linear kinetic energy and the rotational kinetic energy. Add those together, we get 1 mvr. A half plus a half is 1. Again, we can divide by mass on both sides, do some more algebra, and we get that the velocity is the square root of gh. Plugging in our numbers, we now get 4.47. So from this, we can see that the hoop is slower than the sliding block. But we have other shapes that we want to investigate, and so we can continue through them in very much the same fashion. So next we'll do the disc. So remember, this is a solid cylinder, uniform throughout. So very much the same process. We start with the same conservation of energy. We have a different moment of inertia because it's a different shape, but we do similar substitutions. Plugging all that in, simplifying, we get down here with 3/4 mv squared. Again, dividing by the m, and we get a velocity term of v is the square root of 4/3 gh. Plugging in, and we get 5.16. Okay, remember to pause as necessary so that you can write down the important details. Okay, next we have the solid sphere, again following the same process. The only main difference is a different moment of inertia. Everything else follows the same pattern. We just end up with a different number that makes its way through. So we get a velocity as the square root of 10/7 times gh. And this we get a velocity of 5.35 meters per second. So just a little bit faster than the disk. And then for our fifth and final shape, we have the hollow sphere, which sounds cool. This one is just like the others, but I would like you to try. So please pause here and try to figure out the answer, and I will show you the answer in just one moment. All right, hopefully you tried this on your own. Here is the solution that I came up with. Hopefully it matches with what you have found. Okay. So in these equations, you might have noticed that the mass does not affect the velocity because the mass cancels out, and the radius does not affect the velocity because it cancels out too. So it doesn't matter what the mass or the radius is, the velocity is not affected. So if the velocity is not affected, that means the time is also not affected. So, speaking of time, let's go through this big process to find the time. So, to find the time, we know a bunch of information, so this becomes a basic motion problem. So I've listed all of our terms. I picked the velocity of our hollow sphere to use just for this example because it was the most recent. And we need to solve for the time. To do that, I also needed to know the final position, so how far it would roll down the ramp, and I used the geometry of the ramp to do that because the angle and the height of the ramp were given, so I could solve for the hypotenuse. Okay. So if I'm ultimately trying to find time, I don't have an equation in my equation packet that tells me how to do that, but I could figure it out if I needed to, but I might as well just work my way through using the equation packet equations. So I'm going to solve for the acceleration first, and that'll allow me to solve for the time. So I'll pick motion equation number 3, plug in what I know and solve, and I get an acceleration of about 3 meters per second for this particular object. Then once I know the acceleration, I can plug that back into either of the first two equations. I picked the first one. Plugging that in, and I get a time of 1.63 seconds, or more generically, fit that in there. We can take that equation, rearrange to solve for time. I get the difference in the final and initial velocity divided by the acceleration, and that will give me my time as well. Plus, there are other ways that you could go about solving this, since we know a lot of the information already. So from this information, we have solved for the velocity. We know how to solve for the time, so we can figure out, of our 5 objects, which one will get to the bottom of the ramp first, which one will go faster, and a lot of the details that go along with this. Remember to go back and rewatch and pause as necessary. If you have questions, all you have to do is ask. Good luck, everybody.